please join me in welcoming Dr. Chiappe and his hawk, Natalie the Green Dinosaur, from ground to mount.
Thank you. The green dinosaur. So in, I don't know, the next 30 minutes or so, I'm going to be telling you about a dinosaur journey. A journey that goes from the ground in a remote area of Utah to the mount that on November 17th you'll see here at the museum. Now our journey begins 150 million years ago. Just to put it into context, the saber-toothed cats and mammoths from the tar pits are 20, 30, 40,000 years ago, right? T-Rex and Triceratops lived 66 million years ago. This animal, Natalie, lived 150 million years ago. So much, much older than T-Rex. And our journey will take us from Los Angeles to the southeastern corner of Utah and back, right? So back in, the late Jurassic, when Natalie lived in southeastern Utah, the landscape, as I, have here in that little reconstruction, was very different from, the landscape of the Colorado Plateau that we see today. It was much more green. There were, large rivers going through big open plains. There were big trees and big dinosaurs, right? So at the time, some dinosaurs died and were washed into a riverbed and got buried in the riverbed over millions of years. The bones became replaced by minerals, they became fossilized, petrified, and then through erosion, they were exposed the way you see here. Now, how are dinosaurs found? This is a question I, get asked all the time. So first, it is important to know and to study the rocks that are in the region that you're going to be exploring. This is a geologic map, right? What it maps here, the different colors, are rocks of different ages and different types. In this particular case, the rocks in green are from the age of dinosaurs. You need to know then what kind of rocks you have in the area you're going to explore, understand the age, understand the type. Dinosaurs were terrestrial animals, land animals. They did not live in the ocean, so you may not want to look for dinosaurs, say, in rocks that were formed at the bottom of the ocean, because it's very unlikely that you're going to find them. You'll find other things, but not dinosaurs, right? So if I were to ask you guys, and here's a show of hands, where would you look for dinosaurs? Would you look for dinosaurs here, or would you look for dinosaurs here? Let's see. Who would look for dinosaurs here? Who would look for dinosaurs here? Exactly, right? Because those rocks on the surface are exposed, and finding dinosaurs entails walking around and finding a little tip of bone, and that tip of bone may lead to a whole skeleton, it may lead to multiple skeletons, or it may lead to nothing, maybe just a broken piece of bone, right? So that's exactly how dinosaurs are found. Walking on the naked rocks of the right age and the right type, and then finding, with some luck, a tip of bone, like here in 2007, when we found the first exposed bones of what would become the Natalie quarry, and what ultimately led to the Natalie skeleton that you're going to see on November 17th. How are dinosaurs excavated? Well, certainly not, the way we see it in movies, like Jurassic Park. That is fiction. Dinosaur excavations are far more complicated than, you know, Jurassic Park. Often you have landscapes like this, you know, where you have all those boulders that are on top of the bones and the rocks that contain the bones. You have to get those boulders out and clear the area, sometimes by hand, sometimes by, you know, heavy machinery. I'm looking at this picture, you know, that I don't know, maybe is from 2008 or something like that. 5 weeks ago, I had back surgery, and now I'm saying, I get it. So that's an advice for the young paleontologists. So, you know, and then obviously the team is going to be working with tools of all sorts, sometimes jackhammers, shovels, pickaxes, and so on. Slowly, the quarry is going to grow. You're putting your tents. You see, you know, more of that, more of the work, and the first bones that look pretty nice are becoming, you know, visible. You see part of the tail of a long-necked dinosaur there, a sauropod. A femur, the thigh bone of another long-necked dinosaur, right? And eventually the excavation turns into some form of a small compound there, you know, with tents and tools and people coming and going and so on, even a parking lot, like here, right? So once the bones are exposed, it is critical that you document them well before you pick them up, right? So you measure them, you document aspects of the rock that has entombed them and the position that they're found. So we often do these quarry maps. You can see here people working with a grid and measuring the depth, drawing the position of the different bones. Nowadays, you know, sometimes we would just scan the entire surface, but I think that there's still a lot of value in going, you know, old school in doing things like this and making sure that every bone is well labeled and well documented, and eventually you're starting to build a map like this, right? By hand, usually, you know. Eventually this bone will become digitized and fine-tuned. And here, for example, I'm showing you a portion of the Natalie quarry. After multiple years of work, you can see the different colors, you know, show different types of dinosaurs and specimens. But you can see that the quarry map here is, you know, composed of hundreds of bones that are all jumbled together. This is what we call a bone bed. This is the result of, you know, centuries of animals dying and being washed into the riverbed and, you know, getting one pile on top of the other. There's also a significant amount of time contained here. This is not something that happened overnight or in a day, like a flash flood. This is a process that, you know, took probably centuries, and that's what we call time averaging, right? But imagine that, say, 500 years, that sounds like a lot for us, you know, when you're talking about 500 years, or when you're talking about, you know, distinguishing between two events that are separated by 500 years, 150 million years ago, that's just like, you know, an instant, right? We do not have the resolution that can allow us to tell two, you know, separate, say, entombments of, you know, two animals that maybe died, I don't know, a century apart, for, you know, a bone bed that is 150 million years old, like this one. Once all those bones in the quarry is well documented, then it's time to pick them up, right? So often we work with burlap. Here it's been soaked in water because then we're going to be adding plaster, and we're gonna cover the bones with tissue, and then we're gonna surround them with this plaster and burlap, and we're gonna create the things we call jackets, which are essentially this mummies, if you want, of plaster that inside contain rock and the bones that are inside that rock, right? And as such, we're going to pick them up, cut them, and you know, bring them on pickup trucks and bring them to our camp. Sometimes on a pickup truck, if it's too big, we need something bigger, right? Like here. Back in the camp, we want to make sure that all of them are well documented. Once again, that we don't lose any data. And often you end up after, you know, a month with something like that shows you, say, you know, all the jackets that were collected in, you know, maybe 4 weeks of work. When you put all the years we worked together at the Natalie Quarry, we're looking at hundreds of jackets like this containing many bones that were excavated over more than a decade. Once the jackets are here, then we have to prepare them, right? And we do that in certain labs or certain spaces, sometimes outdoors, because sometimes some of the process of prepping them is very messy and dusty. You may have seen how our preparators, our paleontological conservators work on bones in our dino lab on the second floor, and if not, you know, I will encourage you to go and see that today. This is back at NHM here in one of our decks where you can see some of these jackets being opened, so the plaster is being cut to expose the rock. You could see here one of our preparators working on the trunk of Natalie, and you know, and as you can see, the edge is the plaster jacket that's being cut, so the bones are still resting on that. In time, they're going to be completely extracted and protected to be mounted, in the case of many of the bones from the Natalie Quarry, in the Natalie skeleton, or, you know, to be studied. And here's the dino lab, and here's just another, you know, type of scene of prepping these bones. Once the bones are prepared, right, our journey now takes us to the next step. And the next step is to curate those bones. In other words, to ensure that they are identified, that you know whether this is a carnivore or is it a herbivore, a long neck, or some other kind, or armored dinosaur, some other kind, that they're all cataloged, you know, that, you know, we understand again what exactly these bones are, because they do not come with labels, right? And then that they are stored in our collections. Some of them, of course, will be then taken to compose a mount for display. Okay, so now finally we're back to your question, right? You know, you asked me whether, you know, Natalie was what kind of species, right? What type of dinosaur is Natalie? Well, if you look at the tail and some of the legs of Natalie, they look like a dinosaur called Diplodocus, a dinosaur that I'm sure most of you know of, right? But if you look at the neck of Natalie, it looks like a different type of dinosaur. It's much longer than that of Diplodocus and different. It looks more like an animal called Barosaurus, related to Diplodocus, but different. So Natalie is actually a new species of dinosaur, and it combines the neck of something that looks more like a Barosaurus with the tail and trunk of something that looks more like a Diplodocus, right? So that's what it is. We do not have a scientific name for Natalie yet, but we do know that it is something new to science. What kind of other dinosaurs live with Natalie? Because as I mentioned, that quarry map has hundreds of bones of many different kinds of dinosaurs. So when you start looking at the bones that are coming out from the quarry map, we can tell that there are at least 3 different species of sauropods. Natalie, another much bigger long neck that is probably Diplodocus, and another kind of quite different long neck dinosaur that is more like a Camarasaurus. Right? We also have carnivorous dinosaurs, we have armored dinosaurs, we have plated dinosaurs like Stegosaurus, you know, and we have a bunch of little bipedal plant-eating dinosaurs as well. All part of that ecosystem that lived, you know, 150 million years ago in southern Utah. Here are some of the Diplodocus-like animals. The 3 from the bottom are Natalie, or the species that Natalie belongs to, right? The bigger one is more like a Diplodocus. Here's a Camarasaurus. Here's some of those meat-eating dinosaurs, theropods. Here's some of the little small plant-eating dinosaurs. And here's a little pie chart that shows you more or less, right, the sort of like abundance, the relative abundance of the different types of dinosaurs. And as you can see, this is a quarry that is very heavy, very rich of sauropods, the long neck dinosaurs, the Camarasaurus and the Diplodocus, right? That's what really, the big guys, what really makes the bulk of the bones that are found there. Now, of course, the inescapable question: why is Natalie green? And seeing some of the bones that are out there in our tables, all the bones from the Natalie quarry are green. Not just Natalie, all of them, because they were all affected by the same geologic process, right? So what happened is that when Natalie, well, first let me tell you that that is highly unusual. We're going to have another talk by another expert who has seen more Morrison Formation dinosaurs than probably anybody else in the world. And for the most part, you know, and I hope I'm not wrong, for the most part, they're black, they're brown, sometimes they're a little green, but they're not green. And, you know, and that's what we're saying, that Natalie is the only green dinosaur mount, there may be a bone here and there, but green dinosaur mount in the world. And we're very proud to have it, you know, here at the Natural History Museum. Now, going back to the question, why? You know, why does it have this color, right? The reason is, the answer is, because of the types of minerals that replace the original fabric of the bone, right? Now, this didn't happen when the animal died 150 million years ago. When the animal died 150 million years ago and eventually became fossilized, I'm going to assume that those bones maybe look like brown or black, like many other bones from the same rock layers that are, you know, across Utah and Wyoming and many western states, Colorado. Millions of years after this animal had fossilized, there were geological processes in that area that led to a replacement of the original minerals. And those minerals were replaced by a kind of green mineral called celadonite. Here is a celadonite specimen, for example. You know, not bone, just the mineral, right? The kind of mineral that you could see in our mineral hall. Celadonite also, perhaps, you know, I guess maybe is better known by many of you in the form of celadon, which is a type of pottery very common in Asian countries, and, you know, of course, is green, just like Natalie, right? And the mineral. So that's the reason why this dinosaur is green. So make sure that you come on November 17th you check out the current issue of Nat Geo magazine and also the Nat Geo Kids for stories on Natalie. At least this magazine here, the main magazine, is available in our store if you want to pick up a copy of it.